With this problem, we can get some practice dealing with static friction and also objects on an incline. So press pause, do your best. If you have no idea what to do, at least try to write a free body diagram. At least try to work with the free body diagram. Once you get your free body diagram, you can just at least write a net force equation or two. If one for the x direction, one for the y direction. Once you do that, you can maybe figure out what your net force should be equal to in the x and y directions. I'll give you a hint. It should be 0 in both directions because we don't want this object to accelerate. And then you might find that you could just solve the rest of the problem, even though you felt like you had no idea what to do. Okay, so press pause, take some time and work through it. So I'm going to start with a free body diagram, and I'm already going to have my force of gravity, mg, split into horizontal and vertical components, and I'm already going to tilt my axes so that the normal force is pointing up. If you're not sure how I got to here, go back and watch the videos on the objects on an incline. Watch those videos a few times and then come to here. Okay, so I'm going to start from here from now on. So I know I'm dealing with friction, so I'm definitely going to need to know what my normal force is. So I'm going to look at my net force in the y direction. My net force in the y direction is equal to n minus mg cosine theta. And my net force in the y direction has to be equal to 0 because we're not going to accelerate in the y direction. That lets me say that my normal force is equal to mg cosine theta. And as I said, you might get so used to doing these problems that whenever you see an object on an incline and there's no other forces in this direction, you might just be able to look at it and say, I know that the normal force is equal to mg cosine theta because that's what happens when you're on an incline. But here we worked it out. Okay, we don't know any of these values, by the way, so I'm just leaving them as variables. Now let's look at the net force in the x direction. So in the positive x direction, I have mg sine theta. And in the negative x direction, I have this force of static friction. We know it's going to be static because we're trying to figure out, we don't want the object to slide. We want it to stay stationary, so I want to be using static friction. The net force in the x direction also has to be equal to 0 because we're not going to accelerate in the x direction. I want this block to stay where it is. I don't want it to accelerate downwards. I don't want it to accelerate upwards. I want it to stay stationary, so I want my net force in the x direction to be equal to 0. That lets me say that my force of static friction is equal to m times g sine theta. Well, we're going to try and figure out what is the biggest that theta can get. And if as theta gets bigger and bigger and bigger, static friction is going to have to supply more and more and more force in order to keep this object stationary. But we remember that there is a maximum force that static friction could ever supply. So the maximum angle that we can sit at is when static friction is supplying the maximum force it can possibly supply. And the maximum force that static friction can supply is equal to mu sub s times n. Let's plug in for mu sub s because I do know what that value is. And let's plug in for n. So I have 0.5 is my value for mu sub s, my coefficient of static friction. And my normal force that I found up here is mg cosine theta. So a couple things happen here that's interesting. First of all, the mass cancels out. That means that it doesn't matter what the mass of this object is. The maximum angle that this can sit at is independent of what the mass of the object is. It only depends on the coefficient of friction. Okay, G also cancels out, which means this doesn't matter even if we're on Earth. This would be the same angle if we were on the moon. Solving this, we get that our angle theta is equal to 26.6 degrees. So any objects that are wood sitting on wood, any wood on wood objects have an angle. The maximum angle they can sit at before they slip is 26.6 degrees. And this is called something interesting. It's called angle of repose. I just want to mention this because I think it's really interesting. You're not really going to be tested on something like this. But that angle that we just found here is called the angle of repose. What's the maximum angle that this block can sit at without slipping? And so objects like, a wood block sitting on a wood surface has an angle of repose, but also granular material have a single angular of repose. So, one thing that makes sand dunes look so cool is that you might not realize it, but these sides are always symmetric and they're always the exact same angle. Whenever you look at any sand dunes, the angle that's made is exactly the same. This is, I think, sugar. And if you pour sugar out, it will always, always, always make the same angle here. Because if the angle got too steep, then the sugar would fill in. Okay, this is rice. Rice like this will always stack at this angle, always. Here's some angles of repose for different materials. Another thing you can look at that's interesting is just the difference between dry soil and wet soil. Why does that matter here in California? It matters if you live near a cliff, because the natural angle that's going to form between the top of the cliff and the bottom of the cliff, that angle there with that horizontal, is going to be 45 degrees. And that's where nothing is going to slip. But once that soil gets wet, suddenly the angle is 34 degrees, which is a much more shallow angle. So dirt is going to flow from the top to the bottom until it reaches an angle of 34 degrees, and that's called a landslide or a mudslide. So you can kind of see the origins of why we have mudslides, but just by looking at these two different angles of repose.